Good afternoon. We are pleased to welcome you to our presentation on optimization of training samples with KLE and mutual information. This work was prepared by Denis Simonov, Alexander Palagin, Igor Simonov, Bogdan Zaika from VM Glushkov Institute of Cybernetics of the NES of Ukraine. The aim of this study is to analyze and justify the effectiveness of applying entropy-based methods for processing and analyzing training datasets in order to improve the performance of machine learning models. To achieve this goal, the following objectives are set. Analyze the capabilities of KLE method for assembling future information in n-dimensional space. Develop a combined approach using KLE and mutual information for future selection to enhance model performance and reduce the resource requirements for solving classification and prediction tasks. The implementation of these objectives will contribute to the development of the methodological foundation of machine learning and provide more efficient approach to training dataset preparation, which in turn will improve the accuracy and generalization ability of modern algorithms. Research goal: analysis and justification of the effectiveness of using entropy methods for processing and analyzing training samples in order to improve the quality of machine learning models. Research objectives: analysis of the capabilities of the KLE method for evaluating the informativeness of futures in n-dimensional space, and development of the combined KLE and mutual information method. The Kozachenko-Leonenko method is an effective approach for estimating differential entropy in n-dimensional space. Unlike parametric counterparts, this non-parametric method does not require prior assumptions about data distribution and performs well even with complex, nonlinear distributions. By applying this method, we can reduce the dimensionality of the future space without losing critically important information, filter out noisy or weakly representative data, form a compact, relevant dataset that enhances model robustness against overfitting, improve the generalization ability of models even under conditions of incomplete information. The basic idea is that entropy is estimated through the average distance to the kth nearest neighbor for each point in the sample. To do this, a minimum radius is determined for each observation within which k+1 points, including itself, are located. Then, using these radiuses, an entropy estimate is calculated based on a formula that includes the d-gamma function, the Euler-Maclaurin constant, and the volume of a unit sphere in the corresponding space. Bootstrap or cross-validation can also be used to increase accuracy. The method allows you to currently estimate the information content of futures, determine this relevance, and thus optimize the training sample. Using of mutual information in combination with the Kozachenko-Leonenko method is appropriate for training sample preparation, as it allows for effective evaluation and elimination of redundant or weakly informative futures, which improves the quality of machine learning models. In particular, mutual information is a powerful tool for dilating nonlinear dependencies between futures and the target variable, which allows for the formation of sample with balanced and maximally useful information. To reduce the dimensionality of the future space while maintaining relevance to the target variable, mutual information is used. Futures are cut off in which the mutual information value is less than the alpha threshold. If the basic selection does not provide sufficient performance, iterative optimization of the alpha threshold or a combined criterion that balance the quality of the model and the number of selected futures can be used. Preparing a training data sample using a combination of Kozachenko-Leonenko methods and programming with mutual information allows you to form a cleaner set of futures and increase the overall efficiency of ML methods in solving prediction and classification problems. One of the important stages of developing effective machine learning models is the validation of results on real datasets, which allows us to objectively assess the impact of preprocessing on the accuracy and robustness of classification. To verify the quality of proposed entropy methods, a comparative analysis of classification result using preprocessed and unpreprocessed training sample was applied. To assess the effectiveness of entropy methods for processing training sample in improving the quality of machine learning models, the gas sensor array low concentration dataset is used. The table shows a slice of the case data. The dataset includes 90 gas samples measured by 10 semiconductor sensors for 6 different gases and different concentrations. Each gas concentration pair have 5 samples, each containing 9,000 data points. Figure A on the left shows that without KLE preprocessing, classification accuracy gradually increases with the number of features, but remains nonlinear and fluctuating. The accuracy starts low and never reaches 1, indicating information loss likely caused by noisy or irrelevant data. In contrast, Figure B on the right shows that with KLE preprocessing, accuracy improves more rapidly. After around 7 features, it rises sharply and approaches 1, suggesting that preprocessing significantly enhances classification quality by reducing the impact of informative features and improving model robustness. In Figure A on the left, without the KLE model shows stable training accuracy and the dataset grows, while cross-validation accuracy increases slowly but remains lower, indicating possible overfitting and the influence of the noisy or unevenly distributed data. In Figure B on the right, the KLE model shows a better balance with high accuracy is reached even with less data, and the smaller gap between curves suggests improved generalization and reduced overfitting due to effective preprocessing. In Figures 1a and 2a, the KLE model exhibits a chaotic and uneven distribution of points with overlapping classes and a fuzzy structure, indicating the pressure of noise and irrelevant information, which complicates classification and reduces the accuracy of the model. In contrast, in Figures 1b and 2b, after preprocessing with the KLE method, the data has clear clustering with better differential between classes and a structured distribution, indicating the effective reduction of noise and improvement of the model generalization. In Figures A, without processing, the prediction time and CPU time increase to 0.67 seconds, which indicates high computational complexity. After processing by the KLE method, Figures B, these indicators are significantly lower and more stable, which confirms the reduction of computational costs and increased performance. Conclusions. First of all, the KLE entropy method effectively improves the quality of training datasets. It enhances objective assessment of future informativeness, reduces the number of features without losing relevance, enhances model accuracy and robustness, decrease overfitting and computational costs. The use of mutual information helps eliminate noisy features. Prospects. Adapting KLE in deep neural networks to reduce feature space. Integrating with active learning, for example, entropy sample for dynamic dataset updates. Development of adaptive algorithms based on entropy and mutual information. Improving model generalization in changing conditions. Future reduction of computational cost during training.